Welcome to my channel on chemistry lessons. Please make sure you like and subscribe to make sure you don't miss out on future content.
So this is a rates of reaction video, and it's actually lesson 2 in the series. So if you haven't watched video 1, go back and watch it. And this video is going to cover a definition of the term order of reaction, and we're going to look at how we use experimental data to determine orders of reaction. So we'll start with some prior knowledge stuff, and then eventually we'll move on to some fairly difficult exam questions, so make sure you stay tuned to the end. Okay, so we're going to start with some prior knowledge stuff. So whenever you see square brackets and a substance inside, so this substance is just substance A, whenever you see square brackets, that means the concentration of that substance in moles per decimeters cubed. So square brackets A means moles per decimeters cubed of A. So math stuff now. Anything to the power of 0 is 1. If you don't believe me, try it on your calculator. Any value whatsoever to the power of 0 is 1. Next up, anything to the power of 1 is that number. Again, try it on your calculator. 5 to the power of 1 is just 5. 6 to the power of 1 is 6. And finally, x squared is x multiplied by x. So 5 squared, 5 times 5, 25. 6 squared, 6 times 6, 36. As mentioned in a previous video, we are now going to be focusing on how the concentration affects the rate of reaction. So we've used collision theory to explain how concentration affects the rate of reaction. However, we're going to start quantifying the rate. We're going to start measuring the rate. And there are many units we could use, but the units we are going to use from now on to measure the rate is the rate of change of concentration, because we're going to be looking at how the concentration affects the rate. So we're going to measure in moles per decimeters cubed per second. That's going to be our units for rate. Now, because we're going to start quantifying rate, we're going to require a rate equation in order to calculate the rate. Now, let's consider a reaction between A and B, a very, very general reaction where A is reacting with B to form some products, and there could possibly be a catalyst C. So here we've got reactants A and B with a catalyst C. Now the rate equation will take this form, where the rate measured in moles per decimeters cubed per second is equal to some sort of constant, rate constant, and we'll look at that in future videos, multiplied by the concentrations of the reactants, and notice how the catalyst, the concentration of the catalyst, can appear in the rate equation. And we've got to the power of something, m, n, and x. And what we're looking at for the rest of this video is how we determine what these values are, this m, the n, and the x. Because we do not derive these values from the equation, as you would do in equilibrium. We don't derive them. We have to actually use experimental data in order to determine these values here, the m, the n, and the x. So these three values then, this m, this n, and this x, they are known as the orders of reaction. So m is the order with respect to A, n is the order with respect to B, and x is the order with respect to C. So a definition for the order of reaction then, so the order of a reaction with respect to a particular reactant, it's the power to which this reactant is raised in the equation. Okay, so let's start looking in some more detail about these terms, these orders here. Now we are going to be limited to using 0 order, first order, second order, which means these numbers are limited to 0, 1, or 2. So it's either to the power of 0, to the power of 1, or to the power of 2. Now let's remind ourselves, anything to the power of 0 is just 1. Okay, so what we're saying here is, if we were to change the concentration of a reactant and nothing happens to the rate, we are saying it's zero order, because no matter what we do to the concentration, if it's to the power of 0, it's just 1, so it has no effect on the rate. So if the concentration was to change, it will have no effect on the rate. So something that's 0 order has no effect on the rate, none. First order, let's remind ourselves of something to the power of 1, is that value. In other words, if we were to double the concentration, the rate would double. If we were to halve the concentration, the rate would halve. If we times the concentration by 0.8, the rate would multiply by 0.8. So we'd say the first order if it's directly proportional. In other words, whatever you do to the concentration, it has the same effect on the rate, directly proportional. So let's look at second order then. Reminding ourselves, something to the power of 2 is that value squared, it's multiplying by itself. So if we were to double the concentration of a substance, it means the rate would go up by a factor of 4. So 2 squared is 4. Now if we were to multiply the concentration by 3, so if you were to triple the concentration, then the rate would go up by 9. It gets a little bit more confusing if we were to use fractions. So if we were to halve the concentration, it would be half squared, which is in fact a quarter. So if you were to halve the concentration, the rate would quarter. It would be divided by 4. Okay, let's take a look at this example then. We've got rate is equal to rate constant multiplied by the concentration of NO squared and the concentration of O2. Now, this is just to the power of 1. We don't bother writing power of 1. So what I can see straight away is it's second order with respect to NO and first order with respect to O2. The overall order would be 3. It's 2 plus 1. So the overall order of this reaction is 3. Second order with respect to NO and first order with respect to O2. Okay, so let's consider this scenario then. What would happen to the rate if the concentration of NO is doubled and the concentration of O2 remains constant? Now, we know it's second order with respect to NO, so whatever we do to NO, we need to square it, and whatever we do to O2, it's to the power of 1. So, we are multiplying NO by 2, but we need to square that. Oxygen is remaining the same, so we're just timesing it by 1, 1 to the 1. That's 4 times by 1, which is 4. So the rate would multiply by 4. So let's consider this situation then. So the concentration of NO is doubled and the concentration of O2 is also doubled. So second order with respect to NO, so we're doubling that, which is timesing it by 2. It will be 2 squared because it's second order with respect to NO. This time we are also doubling the concentration of O2, but that's just to the power of 1, which is 4 times by 2, which is a factor of 8. So in this scenario, the rate would increase 8 times. Now let's have a look at what's going to happen here. So the concentration of NO has been halved and the concentration of O2 has been tripled. So NO has been halved. We need to square that. Concentration of O2 has been tripled, power of 1. Now if you put this into your calculator, a half squared is a quarter. 3 to the power of 1 is 3. 1 quarter multiplied by 3 is 3 quarters. So the rate would actually decrease here. it would only be 3/4 of what it was. So the rate would actually be reduced here.
Okay, so what we're going to look at now is how we can use experimental data to determine the order of a reaction, or the orders with respect to each reactant. Here we have two reactants, A and B. So we know the rate equation will take the form of rate is equal to K, some rate constant. We'll look at that in the next video, multiplied by the concentration of the reactants. And each reactant will have a specific order. So the rate equation is going to look something like that, where X and Y are the orders with respect to A and B. We also know that X and Y have to be either 0, 1 or 2. Now, what we're going to do here is we're going to compare experiments to see what happens to the rate when concentration changes. Let's start by considering experiments 1 and 2. If we look at experiment 1 to 2, the concentration of A is doubling. So A is doubling. So it's 2 to the X. And the concentration of B remains the same, 1. So that's multiplying by 1 to the Y. Now 1 to the power of 0, or 1 to the power of 1, or 1 to the power of 2, they're all going to be 1. 1 to the power of anything is just 1. So I can remove this, which is why I'm comparing two experiments where the concentration of one of them doesn't change. That's essential. We've got to pick two experiments where the concentration of one of them doesn't change. And what happens to the rate when we compare experiments 1 and 2? Well, nothing. The rate is just the same. So what we have here is 1 is equal to 2 to the X. Therefore, X has to be 0. Remember, X has to be 0, 1 or 2. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. So here we have determined that it's 0 order with respect to A. We can actually see that though, because the concentration of A is changing and the rate is not. So changing the concentration of A has no effect on the rate. That means it's 0 order with respect to A. Okay, so we've established that the order with respect to A was 0, which means it does not affect the rate. I have now removed it from the rate equation because anything that's 0 order will not appear in the rate equation because it has no effect on the rate. So what we need to do now is compare two experiments where the concentration of B changes, because I'm only interested in what happens to B now. So let's compare experiments 1 and 3. The concentration of B is going from 1 to 3, that's multiplied by 3. Going from 1 to 3 here, we need to be careful because it's in standard form, so it may appear that it's going down, but actually it is increasing. So it's going to 1.8 times 10 to the minus 3. So I'm going to divide 1.8 times 10 to the minus 3 by 2 times 10 to the minus 4. And you can see on my calculator there that it's going up by a factor of 9. So what's happening here is the rate is going up by 9, B is going up by 3, that's 3 to the Y. 3 to the 1 is 3, 3 to the 0 is 1, 3 to the 2 is 9. So we can see here that 9 is equal to 3 squared, therefore Y is 2. So we have determined that it's second order with respect to B. If we double the concentration of B, the rate quadruples. So whatever you do to the concentration of B, you square it, and that's what happens to the rate. So our rate equation is rate is equal to rate constant multiplied by the concentration of B to the power of 2. So that's our final rate equation there. We have deduced the rate equation for that reaction using experimental data. Okay, so what I'm going to suggest you do here is you pause the video and you have a go and see if you can deduce an expression for the rate equation using the experimental data in the question. And when you're ready to hear the answer, unpause and we'll go through it. So the first thing is that we know the rate equation will take this form. Concentration of reactants multiplied by each other to the power of something. So X is the order with respect to NO and Y will be the order with respect to H2. And we know that X and Y will either be 0, 1 or 2. Okay, so what we're going to do is we're going to find two experiments where the concentrations of one of the reactants doesn't change. In this case, I can see that experiments 1 to 2, the concentration of H2 does not change. Concentration of NO is doubling. And the rate is also doubling. Remember, if you're unsure and you're not so comfortable with numbers, we can use a calculator to show this. 3.76, so that's where I'm going to, divided by where I came from, 1.88 times 10 to the minus 4. You will see on my calculator that it's doubled. So if you take the value that you're going to and divide it by the value that you came from, you will find the factor of which it's increased or decreased by. So the rate has doubled. Now I can remove this from the expression because 1 to the power of anything is 1. So to tidy this up, I've got 2 is equal to 2 to the x. Therefore, x is equal to 1. Remember, it has to be 0, 1 or 2. If it was 0, we'd have 2 equals 1, which is incorrect. If it's 1, we have 2 is equal to 2, which is correct. But if x was 2, we'd have 2 being equal to 4, which is incorrect. So we've determined that this is first order with respect to NO. So we've established first order with respect to NO. So notice how in the rate equation, I have replaced x with 1. But when it's 1, we don't bother writing it, we just leave it blank. So it's first order with respect to NO, and we're unsure of the order with respect to H2. So what we need to do now is compare two experiments where the concentration of H2 changes. So I'm going to compare experiments 1 to 3. What happens here? So 0.75 divided by 0.5. This is going up by a factor of 1.5. And it's to the y. And what's happening to NO? Well, it's going to 1.44, so 0.144 divided by 0.12. So that's an awkward one here. It's going up by 1.2. So NO is going up by 1.2. And it's 1.2 to the 1. So again, we don't need to put the 1, it's just 1.2. What happens to the rate? Well, it goes from 1.88 times 10 to the minus 4 to 5.08 times 10 to the minus 4. So I'm putting in my calculator 5.08 times 10 to the minus 4 divided by 1.88 times 10 to the minus 4. And that's telling me it goes up by a factor of 2.7. So this is much more complicated than the previous example. So what we have now is 2.7 is equal to 1.2 times by 1.5 to the y. So I'm going to divide both sides by 1.2 to remove the 1.2 from the right. So 2.7 divided by 1.2 is equal to 2.25. So we've removed the 1.2 from the right now because I've divided both sides by 1.2. So we know already that it can't be zero order, because if it was zero order, it would be equal to 1, and it's not. If it was first order, we'd have 1.5 is equal to 1.5. We don't. So let's see what happens if we do 1.5 times 1.5, which is 1.5 squared, we get 2.25. So I've just worked out that y must be equal to 2. So it's second order with respect to H2. So our rate equation is rate is equal to a rate constant K multiplied by the concentration of NO to the power of 1 multiplied by the concentration of H2 to the power of 2. Second order with respect to H2, first order with respect to NO, and overall third order. Okay, so final example then. Again, I'm going to suggest you pause it and have a go at yourself first before you unpause the video and then listen to the answer. Okay, so what makes this one a little bit more tricky is that it's telling you there's an acid catalyst present. So the catalyst can appear in the rate equation. So the rate equation is going to take the form. Rate is equal to a rate constant K multiplied by the concentration of I2 to the power of something. Then the concentration of CH3COCH3 to the power of something, but also because we're told it's catalyzed by H+, the catalyst can appear in the equation. And I'm putting that to the power of Z. So this is a slightly more complicated rate equation because we have a catalyst involved here. And as you can see from the experimental data, they're changing the concentration of H+2 to see if it has an effect on the rate. So what makes this a little bit more complicated is we do have three variables here. So it will always be the case that there'll always be two experiments that we can compare where only one thing is changing. It may take you a little while to identify which two, but there will always be two experiments you can compare where there's only one thing changing. Now I can see, I'm going to look at experiments 1 and 3 because I can see this is not changing and this is not changing. I can see that they are the same. So my concentration of this is the same, my concentration of this is the same, and therefore we can remove them from the rate equation. Concentration of H plus is doubling, that's 2 to the Z, and what's happening to the rate? It's going from 9 times 10 to the minus 5 to 1.8, so it's going to 1.8 times 10 to the minus 4. And it's coming from 9 times 10 to the minus 5. Be careful with your standard form. So that's doubling. So what's happening here is the rate is doubling. So to simplify this, 2 is equal to, I can remove this and remove this because 1 to the power of anything is just 1. So 2 is equal to 2 to the Z. Therefore, Z is equal to 1. It's first order with respect to H plus. So we've established first order with respect to H plus. So I've removed the Z from the equation now and replaced it with a 1. So what we need to do now is to compare two experiments where either I2 or CH2COCH3 changes and the other one remains the same. There are lots of different ways I could do this, but I'm going to compare experiments 3 to 4 because I can see this doesn't change and this does change. So I'm comparing 3 to 4. So I2 is just multiplying by 1, that's 1 to the x. What's happening to the CH2COCH3? Well, it's going to 8 from 6, so 8 divided by 6, that's 1 1/3 to the power of y. And what's happening to the H plus? Well, that's just remaining the same, 1 to the 1. And what's happening to the rate? Well, it's going from 1.8 to 2.4 times 10 to the minus 4. And that's 1 1/3. So I can remove this and I can remove this because that's just 1. 1 to the power of anything is 1 and 1 to the 1 is 1. So we've now got 1.33 is equal to 1.33 to the y. Therefore, y is equal to 1. So it's first order with respect to CH2, CO, CH3. So our rate equation is starting to take shape now. We've replaced our y and our z with 1s because we determined it was first order for those two. Now we need to compare two experiments where the concentration of I2 is changing. I'm going to compare experiments 1 and 2 because I is doubling. What's happening here? Well, it's going from 6 to 8, so 8 divided by 6, it's 1 1/3. This isn't changing. And what's happening to the rate? Well, it's going to 1.2 times 10 to the minus 4 from 9 times 10 to the minus 5. It's going up by 1 1/3 again. So the rate is 1.33. So let's tidy this up. We've got 1.33 is equal to 2 to the x. I've missed that off there, so that's 2 to the x. Multiplied by 1.33 multiplied by 1. I can leave the 1 off. So I'm going to divide both sides by 1.33. I end up with 1 is equal to 2 to the x. Therefore, x is equal to 0. So we have just determined that the rate equation is equal to a rate constant. We now know that I2 doesn't appear in the rate equation because it was 0 order and it was first order with respect to the other two. So that now is our rate equation. Done. Okay, so let's finish this video then by looking at the key points. First key point. The rate equation is a mathematical expression showing how the rate of reaction is linked to the concentration of reactants. The rate equation is derived from data and not from a balanced symbol equation. The term order of reaction with respect to a particular reactant is the power to which that reactant is raised in the rate equation. Orders are limited to 0, first or second. And finally, being aware that a catalyst concentration can also appear in the rate equation. And that's the end of this video then. So thanks for watching. Please make sure you like and subscribe.